Hi everyone, we are now going to learn about multiple regression. If you have not watched simple linear regression, you need to watch that first. I'm going to make a lot of assumptions that you know how to do some of this as I make this video. So with multiple regression, we are going to see if several variables, several predictor variables will predict one other dependent variable. All of these need to be, for the sake of what we're doing, continuous data. Especially this one, especially the criterion variable, the y, that's got to be continuous. If it were nominal, we use logistic regression. All of these need to be continuous as well. Now, there are some times where we could dummy code something like gender and give it a 1 or a 0, but we need to just talk about that in a different video or separately. But for now, we're going to work with all continuous variables. Our assumptions are the same as they were with simple linear regression. Normal distributions of all variables, and then Durbin-Watson statistics to show that the variables have normal distributions of residuals. So let's do it. I want to know if, let's see here. I want to know if a number of variables affect the amount of oxygen that I use, okay? So my null hypothesis would be there is no statistically significant relationship between the amount, I would say it like this, there's no statistically significant predictive relationship between a combined group of independent variables and oxygen. So I want to know if age, weight, runtime, run pulse, rest pulse, and max pulse together make a model that predicts oxygen. So I'm going to see if the overall model is significant, and then I'm going to look at which ones of these are statistically significant. All right, so this is from an independent set, a random data set. I'm going to look at distributions, and I'm going to look at all of my variables. They all need to go into Y. All of the ones that I'm interested in, basically all of them, right? Let's say max pulse, yeah. All right, and so I hit OK. I'm going to look at skewness and kurtosis for everything. We're good. Skewness good. Skewness good. Skewness good. Skewness good. And skewness is good. And skewness is good. Skewness is good. Praise the Lord. Now we're going to go to analyze fit model, where we are predicting oxygen. All right, I need to make sure my personality is always standard least squares. Now I'm going to put all of these into here. Oops, I'm going to do them in order. Now, one thing I could do is just hit Control and put them all in at the same time. Okay, so I have all of these in. I hit Run. And this looks very much like ANOVA does, or factorial ANOVAs. They are very much related in a secret universe in this general linear model way of doing statistics. But what this is showing the whole model, and this is what I'm interested in knowing. I'm wanting to know, does this whole model do a better job of predicting oxygen than just using the average of oxygen to predict what oxygen would be for somebody? So what I look at, I need to know, is the overall model statistically significant? I look at the analysis of variance. And what this is really doing is it's saying, is the R squared here, statistically significantly different than 0? Is the variance accounted for in oxygen, is that variance accounted for big enough to be different than 0? So this is showing 85% of the variance in oxygen is accounted for by all these predictor variables. So what do I report? F parentheses 6,24 end of parentheses equals 22.21, comma, P is less than 0.001. So it is a statistically significant model. Then I'm wondering, well, which ones are statistically significant? And I'm going to have to close my door. There's some people. Okay, so I look right here and I ignore the intercept. And it's showing that, again, these are unstandardized beta weights. So this is saying that all together here, as oxygen, always get this mixed up. Now, as age goes up by 1, as you get 1 year older, your oxygen level decreases by negative 0.22. As your weight goes up by 1 pound, your oxygen goes down by 0.07. That's not very much. Okay, that's what all of this is saying. Now, these t-values again are saying, is this slope statistically significantly different than 0? And it is. So that means that which factors, which predictor variables are significant in this model? Well, depending on my alpha, it would be age, run time, run pulse, and max pulse. Those are the statistically significant ones. I also like to look at the standardized beta. Now listen, last time in simple regression, I told you these were just like Pearson R's, right? Well, here, these are just like partial correlations. Remember the vacuum cleaner? I've got my dust buster right over here. It's like this is showing that that the clean, true version of already accounting for all of these with each other. So this is basically showing the partial correlation between age and oxygen when all of this is accounted for. This is showing the partial correlation between runtime and oxygen when all these other factors are accounted for. Isn't that awesome? So that's what you do here. It's just so exciting. Now don't forget about the other third assumption, the Durbin-Watson. So we do the same thing as what we did before. Okay. And I would have to go back and look at what my numbers are supposed to be. I think that's supposed to be between a 1.5 and a 2.5, and it is. This is supposed to be between a 0 and a 0.5, and it is. This is supposed to be above a 0.05, and it is. So my third assumption is correct. Now let's take a little bit of time talking about how we write this up. If you're ready to get off this video and you can just read this yourself, you are free to do that. But I will take a moment and talk about how to write it. I'm going to pause the video for just a moment. Okay. When we talk about effect sizes for multiple regression, we're really looking at the R-squared value. And remember, R-squared is saying how much of the variance in Y is accounted for by the variance in X. All right. So when you write this up, you are talking about how your assumptions were resolved. We had a linear combination of several variables, and I have that R-squared value there. This is the F value from the analysis of variance table. And this is usually, I think, the number of predictor variables minus 1. This has to do with the number of people you have. And so you only report what your statistically significant ones were. And I usually see most people report the standardized betas. And I forgot to say this. This is really important to look at the standardized betas in the model because it's putting them all in the same level of language. Like age is developed, like age is measured by years, right? And runtime is measured by minutes. And so when we put it into beta, it's like we're leveling the playing field for units of measurement, and we can actually see which predictor variable is truly a bigger contributor in the model. So I would report the unstandardized regression weight. That should be standardized. No, unstandardized. No, standardized. Okay. Unstandard, and if you want to report the unstandardized one, you can. Okay. All right, I'm glad I caught that. So hopefully this is making sense on what you do. I will show you of how you would need to do this if you have several variables. You would have your predictor variables here. This is the unstandardized parameter estimate. You report the standard error. This is basically the standard deviation of this. You report that standardized beta weight, the T, the P, and the adjusted power as well. And just about everything I write, I use that. I'll actually briefly show you, well, I don't have it pulled up, but one of my most recent articles, I have tables just like this. All right, hopefully that makes sense to you guys, and I hope you guys have a wonderful day.